Hi, everybody. Hear me okay?
Yeah,
Yeah, great. Good to see you folks. Thought we'd do today's lecture from merry old England. Um, how's it going? You guys hanging in there? Yeah. Uh, Zoom does get a little exhausting after a while, doesn't it?
it really does.
Yeah. I mean, I think once you get going, it's fine. Once you like either get going in your class or your meeting or whatever, it's okay. You kind of click into it, but to kind of boot it up and kind of start and all that takes a little energy. I completely understand. You folks aren't teaching though, right? So that's nice that you don't have to deal with it yet. So that's good. You guys able to go on campus yet? Anyone been on campus? No, still
I
okay.
went yesterday
Oh, yeah.
to the
Oh.
clinic, so
Was David there too?
no, I just went to the dentist actually.
There's a dentist on campus. I didn't even know that. See, I learned something today, so it's not a total loss. Yeah, I'm going tomorrow. I'll put a word in to folks in the area about if they have a chance to open up the labs, just to have you kind of come in every once in a while. I know it's been kind of kind of difficult to imagine yourself in grad school without coming on campus. So it's kind of a nice thing. They just kind of changed the requirements for being allowed on campus, but they're not that much more strict. At least not for you folks. They're more strict for the faculty. We have to now to open up the labs. We have to have cleaning supplies in very specific spots so you can come in and do all your cleaning before you sit down and all that sort of stuff. But hey, whatever it takes. Okay, let's see. Zoom has been updated recently, and they've kind of shifted around some settings. So I want to make sure that everything's working. I've got some demos today that are actually absolutely going to depend on you being able to hear them. So hopefully I've fixed everything. I've been having trouble with that in my other class, but you let me know if there's any problems at all, either with the quality of the images or the sound or something like that. Okay, I'm happy to stop and fix it, so I make sure that you folks have the demonstrations that I want you to see. Boy, it looks like it's nicer in England today than it is here in Los Angeles. So okay, then let's remind ourselves. Oh, this is the third lecture coming up, right? Is that correct? Yeah. So we're fine. We're doing really well, actually. You don't have your midterm until we thought maybe week 6. So after the 5th lecture would be a good time for your midterm. So we're perfectly on schedule. So that's not going to be a problem. If there's a little bit of a delay, that's okay too. I'll make sure that you're given enough time to do the midterm so it doesn't interfere with your other midterms, which I believe are pretty much just stat this year, correct? You have a stat midterm in week 5 or 6 or something like that. Yeah. Okay. Well, we'll make sure that you don't have too much overlap in time, so you don't have sufficient study time to take care of this exam. Okay. Any questions? Everybody else happy? Yeah. Okay. Morgan, I like the puppy dog in your Zoom image. That's very cute. Is it still a puppy or is it now a big dog?
No, it's now a big dog.
That does happen. And it looked like that was going to be a very big dog. Is that the case?
Yeah.
Yeah. Okay, that's great. All right. I think dogs are becoming quite famous during Zoom. People are just bringing their dogs in just for a change of pace. So maybe my dog was just in here, but he just snuck out. So next time he comes in, I'll show you mine. Anyway, okay, then let's go ahead and start where we left off last time. And just to remind you, there he is. That is Kohler. That's my German. Uh-oh. What the heck? Yeah, there we go. One of the Gestaltists, and we left off at the Gestaltists. We were, of course, going through the history of perception, and in so doing, also going through cognitive science a little bit. And we left off at Kohler, who was one of the Gestaltists. To remind ourselves, Gestalt was kind of a kind of alternative to structuralism, in that they thought that the structuralists were really concentrating too much on the kind of the the microscopic aspects of the stimuli, and that there were many examples that our friend Wertheimer and Aaron Fells pointed out to us, where it seemed that an understanding of what the kind of elements, the atomisms of the stimulus, weren't going to be sufficient to explain perception. And so for the Gestaltists, the emphasis is on the organization, the entirety of the stimulus, and then how some sort of organizational principles seem to be applied maybe in an automatic fashion, so that what we end up with is something in many cases categorically different than what would seem to be made up by the elements. And you can just see this example right here with the deer with the antlers as just a prime example of that. And what Kohler wanted to remind us here is that somehow we needed to explain how that organization got there. So, one of these beautiful questions, why do things look like they do? Maybe getting more specific for the Gestaltist case, how does the stimulus have, or how does the perception have organization? Why do things look like they have organization? And so Kohler said, well, there's three places that organization can come from. When we talk about perception, it can come from the distal stimulus, it can come from the proximal stimulus. And if you can't see an inherent organization in either of those things, then the perceptual process needed to apply an organization. And he said that's going to be, it would seem, something that the brain would help out with. And so, he talked very, thoroughly about how the distal stimulus doesn't have organization in and of itself. And the proximal stimulus, if you really do an analysis of it, it's just really a mosaic of points that are, kind of made up of the retinal cells. And neither of those things really have an inherent organization. So that organization that is providing the basis for, being able to perceive in a veridical way must come from something else. It must come from the brain. And so just by rejecting 1 and 2, whether or not you agree with that, it's okay. But he turns to the brain states for the thing that imparts the organization. And the other Gestaltists agreed with this, that, yes, we must concentrate on the whole, the organization, as perceptual psychologists, to really understand what's going on. But when it comes to understanding the basis of that organization, it's got to be something in the perceptual process. It's got to be something from the brain.
Can I ask a quick question?
Yes.
Sorry, you said veridical. That is kind of like, can you define that real quick?
Yeah, in this context, I just mean that it's something, it's true to the world, at least true enough to the world, that it allows us to perceive and behave successfully. Okay, vertical. I'm glad you asked that question, because it can mean different things in different contexts. It can mean that we have access to the true world, and I think here I probably mean it. The Gestaltists would mean it that there is an apprehension of the real world to the extent that it is functionally supportive of behavior and perception. Okay, so yeah, we can say that the brain states are providing that veridical contact, the ability to perceive the world in a way that allows for successful behavior. Okay, so it's the brain that must be giving that. And it's doing so through the organizational principles that they so carefully identified. So organization, the bedrock of successful perception, comes from the brain. Okay. Any other questions at this point? Okay. Then let's talk about the brain from the perspective of the Gestaltists. And we're talking about the early 20th century. And so, clearly they don't have a lot of the methodologies that we have now, but they had some interesting things. And you're going to see that there's a kind of, I guess, approach to the brain that is in some ways very modern. And I'll show you what I mean by that. At first, it's going to seem, maybe a little bit loose and a little bit, I guess, amorphous. But I think you're going to see as we go through it that in some ways it's more modern than maybe the approach to the brain that you may have learned as an undergraduate even. So the question is, for these folks, what are the brain states that allow for perception? Along with that, what are the brain states that allow for the laws of organization to be manifest, to be something that act on the stimulus? And here we're going to see an interesting intersection. So remember we talked in the very beginning of the quarter of how perception kind of lies at the intersection of other sciences in some really interesting ways. And here we're going to see an intersection of biology and physics. And you're going to see an approach to, in this case, the neurophysiology, that's what I mean by biology in this case, that's going to borrow from physical principles. We'll come back to that later, but I wanted to kind of point that out as we go through. And it's not often something you see explicitly addressed in, many other theories of perceptual psychology, or many other theories of neuroscience. Say, of course, neuroscience has to be based on biology, chemistry, and ultimately that's based on physics. The physical laws have to apply to the biology in the context of neurophysiology, certainly. But here you're going to see that application kind of takes a more global form, kind of a more I guess you could say macroscopic form, and you'll see what I mean as we go through it. Okay? So, for example, the Gestaltists discussed something called the isomorphism. Sorry, my notes are different from the slides. Let me just check this out. Yeah, okay. So let me, I apologize. I have older notes in here and I did change the slide. Okay. So here's what they thought, and this is actually going to address something that discusses the intersection of biology and physics as I just laid it out. During their time, they were trained in physics and they were buddies with the physicists on their university campuses, spent a lot of time with them, and they knew at that time there was kind of a shift, like. Not unlike the Gestaltists shifted away from the molecular and kind of moved a little bit more towards global thinking about the level of nature they were analyzing. The same thing was happening in physics, where kind of the more molecular aspects of physics were certainly being addressed, but there was also a kind of a camp of physicists that were looking at kind of the more global aspects of physics. And you'll see what I mean by that in just a second. But what they thought was the best way to capture what was going on in the brain was not a neuron by neuron sort of analysis. Like they considered perception as being something that concentrated on the whole, the kind of the kind of more global aspects of the process. They thought that was not a bad way to think about the brain. And so what they kind of started with was the assumption that the brain can be thought of as having its own kind of dynamic principles. It's part of nature, it's part of the physical world. And yes, we often think about brains as being computational systems that involve one neuron affecting another neuron and on like that. You can also think that the brain, even without conceiving it as a kind of coder of information, can be thought as kind of a neurochemical sort of dynamic process that's going to have its own kind of style of dynamics. And so you'll get this more in just a second. What they said is, okay, let's remember that the brain is part of the physical world, and systems like neurochemical systems, electrochemical, magnetic, electrical systems overall have an inherent dynamics to it. Okay, so for example, field theory, and this is what they borrowed in a way from the physicists at the time. I'm not going to go through any details on field theory. You probably know as much, if not more, than I do. But the physicists of the time would talk about the way you can describe something like a magnetic field, an electrical field, using different potentials and kind of kind of vectors of influence or force or something like that, and in some ways describing a system as a field captures maybe some more of the important properties than trying to do an analysis by analysis of very, very kind of molecular aspects to it. So you can apply the same principles to electrical systems and magnetic systems, right? And so, for example, I like to give this example in my undergraduate course. I'm not sure if it's going to work here, but I'll give you an intuition. When I was a kid, we had something. So we didn't have the internet. we had magnets. We had a lot of other things, but everything was very kind of material, tangible for us when we were little kids playing with things. There was no computer games, or there was nothing you could hook to the TV and play with or anything like that. So we had things like magnets, and we did have Legos and Tinker Toys and stuff like that. But magnets were a pretty popular thing. And I remember when I was a kid, I had this kind of I guess anthropomorphized sort of magnet called a monster magnet. And basically, it was just kind of a big red thing that was made out of plastic, and it had two kind of strong magnets down at its fists. So it was in the shape of something that looked kind of like a monster. Its fists were magnet. And I would play with it. And one of the things it said in the package is, oh, go ahead and play with paper clips. And you can see that the monster magnet is so strong, you don't even need to touch the paper clips in order to change their arrangement. And it was absolutely true. You take your parents' paper clips, you dump them on the table, and then you take your monster magnet, and you see the paper, without touching the paper clips, the monster magnet is able to shift the paper clips around a little bit. And you can put down one arm, here I am, the monster magnet, one arm, the monster magnet, and see that the paper clips kind of rearrange themselves like this. So they kind of make more or less some sort of flower pattern. Or if you bring both of the arms of the monster magnet down towards the table, the paper clips will arrange themselves around 2 points. And that might look something like this. Okay, so these are showing kind of force lines of magnetic or electrical fields, this sort of thing. And, clearly, okay, so we did get bored with this after a few times, but still, it looked like a monster. The point is, though, what you would notice is, you kind of apply the monster magnet to the field, and the paper clips would kind of rearrange themselves and make a kind of quasi regular pattern. Didn't work that well, and then it would sit there. And so what you could do is basically you could change the arrangements of paper clips using one a part of the monster magnet, another part, release it, and they would kind of fall away and all that sort of stuff. And so we didn't know it was called this at the time, but what fields do is they try to reach equilibrium. Okay, and we have intuitions about this sort of thing. Sand castles can be considered a kind of a organization that, as the water comes in and kind of ruins our sandcastles, it brings the sand down to equilibrium, right? Equilibrium is kind of the most stable state a field could be in, whether it's a field of paper clips, electrical field, I guess a sand field, if you want to call it that, or what they considered the physiological dynamic field of the brain. So what they're doing, and this is where kind of physics is being applied to biology, without considering the kind of molecular force from one element to another. The one paper clip affects another paper clip, affects another paper clip. Yes, you can do that. You can discuss that. You can describe what's going on with the interactions of the paper clip, but that's not really capturing the most important part of what's going on. What's going on is that the magnet, or an electrical potential, or a neurophysiological potential will structure the field dynamics in a way that's the same in all those different cases. And that's kind of what physics was doing there. They say, cool, all these things act like fields, and they all have the same properties, and they all seem to be moving towards new equilibrium states as different sorts of potentials affect those fields, right? And so what we're doing here is we're finding kind of principles that are true of physical systems and applying it now to the brain. So we know actually that magnets do affect the brain, and electrical potentials do affect the brain, but they were actually more interested in how, I guess we could say, stimulus potentials affected the brain. They were wondering if they would have success in describing an inherent physiological dynamics of the brain that were reorganized by the input, the stimulus input. So it would kind of induce a new equilibrium of the brain state. Okay, so they're trying to see if they can understand perception and the brain basis of perception and perceptual organization by understanding the equilibrium tendencies of the brain. Okay, so let's talk about this principle now, what they called the isomorphism principle. And I'm trying to portray it here in the image below. Imagine that we have a person, a perceiver, looking at that triangle with the missing segment in it. What happens? Well, it acts as a stimulus to the brain, I guess you can say, or a potential to the brain's, physiological dynamics. And what that does is it kind of reorganizes the brain states such that it's going to reach its most stable configuration. Now, what they'll say is that stable configuration is something that's closest to an actual triangle. Okay, now they didn't get into a lot of detail of what exactly was going on neurophysiologically, but they did want to say that whatever it was going towards stability. Okay. And that move in the brain towards stability, equilibrium, was then matched by our perceptual experience. Okay, so you can see they're not only taking a Gestaltist approach to our perceptual experience, they're taking a Gestaltist approach to the neurophysiology in a way. They're saying that there's kind of a global kind of field dynamics in the brain that's moving towards equilibrium, just like all other field dynamic systems, right? And then what they say is that move towards stability, that move towards equilibrium in the brain is accompanied by, is isomorphic to our perceptual experience. So the reason we would classify that input as a triangle with a missing piece, rather than, remember we said that this could, when we were talking about that closure organization, we could say that this could be portrayed as two brackets facing each other. That's not a stable state for the brain. That's not a stable interpretation of the brain. And that interpretation is, in fact, based on the stability the brain is going towards, which is kind of cool. So what the isomorphism principle says is that the perceptual state is isomorphic with the brain state when it comes to moving towards stability. Okay, so let's say it now kind of, as an overarching sort of principle. The simplicity, the I guess stability, the equilibrium nature of all those organizational laws are based on the equilibrium tendencies of the brain. And so the laws the perceptual laws go towards simplicity in their organization because the brain's moving towards simplicity in its electrochemical dynamics, its physiological dynamics. Okay, and that's the isomorphism principle. Okay, so it's really a very, very interesting way of kind of approaching neurophysiology, isn't it? And this is what I mean. So if you go back and look at what's on the top right of the slide here, this is an intersection of biology and physics that is kind of different from how you might expect it. Certainly you talk to any neurophysiologist, they'll say, yes, the neuroscience, the neurophysiology needs to follow the laws of physics. But here they're saying, yeah, it can, yeah, let's make sure it does. But if you can apply field dynamics, right? And in some ways, field dynamics is a more productive, it's a more, I guess, valid description of certain, systems like the magnetic fields, electrical fields. Why can't we apply that to the brain and look to see what the dynamics are there as well? Now, before we leave this, there's a couple of things I wanted to mention. First of all, we will see later on that this is in some ways a very modern, a very contemporary perspective on the brain, where I think a lot of neuroscientists, if you talk to them now, are moving away from kind of a computational model of neurophysiology and looking more at kind of the systemic aspects that representations of things are kind of spread across different regions of the brain, and there's a certain kind of plasticity. So yeah, in some ways you can say that this kind of presage neuroplasticity, where the function kind of defines the physiology more than the other way around, right? So different parts of the brain can take part in different functions depending on what the overall functional goal of the brain is. There is that kind of flexibility to the brain. And in some ways, that is much more kind of molar than we used to think of it, which was, kind of a cell by cell sort of, this cell does this cell does this cell recognizes your grandma, this cell recognizes your favorite Bad Bunny song. Bad Bunny. You guys like Bad Bunny? I don't know. All right. Anyway, that is, that's pretty much rejected now. So even though it seems a little, kind of, I don't know, romantic, this idea of the brain being kind of better construed, better interpreted as a kind of field dynamic system, it is something that has kind of carried through to modern brain science, which I think is just really cool. And the other thing I wanted to say about this before leaving this stuff is the idea of psychology in natural law. And it's interesting. Remember one of the barriers to realism we discussed, I think last week we went through those, was that physics is complete and really can't help with cognition or psychology, and certainly perception, right? There's nothing physics can do to help us understand the principles of perception. And what the Gestaltists said back then, which is, we'll talk about it being rejected, but they said that, no, we can in fact apply natural laws, field dynamic laws. Field dynamics is, a very successful way of looking at these complex systems. You can pick that up and apply it to perceptual psychology just as readily as you can apply it to electric dynamics and that sort of stuff. So they're kind of rejecting the notion that physics is something that can't help us. Physics is complete. They're rejecting that. People then rejected Gestalt for a couple, which I'll talk about in a couple seconds. But I did want to push this a little bit, this idea of psychology and natural law, and the idea that things can be borrowed from physics for perceptual psychology without, I guess, a requirement of a reduction through the other sciences. Okay, so I'll get a little slide on this now, and if you have the slides, you can see this. Oh my gosh, and I am missing that slide. Oh no, I think it's this next one. Hold on, just a second. Oh yeah, all right. That's just a picture of me showing Newton being hit by the apple to talk about natural law. Yes, okay, I know why I have that image in. So yeah, this is kind of important. I actually don't have this on the slide. I apologize. This text on the slide. But let's go back to that flow chart. If you have it in your notes, if you have the slide handy, the one I made for Gestalt. Do you remember that kind of specialized box that was just there for Gestalt that really distinguished Gestalt from structuralism? What it said was that that perception was accomplished through innate laws of organization. I think that's the term I used, innate. But I know innate was in there. And I told you we would come back to that term. Here is us coming back to that term. Typically, when we talk about something being innate in psychology, especially in cognition, we talk about it as the animal, the person, was born with the knowledge of how to use the input, how to process the information. Okay, that when we do developmental perceptual or cognitive psychology, we say, oh, look at the infant can do this right off the bat. The infant can distinguish sounds in their language as well as other languages. Isn't that cool? They must be born with the information or the processes required to do so. Okay, they are born with that. They're born with the knowledge of how to perceive certain things. And that is very often the interpretation of the Gestaltists, that if you go through an intro book or you go through these things quickly, you might say, oh, if I had to now categorize the structuralists and the Gestaltists, I would say the structuralists are empiricists. A lot of what goes on comes through the association and the association principles that bring together the little atomisms, the elements of sensation. But the Gestaltists, they seem to be more nativist, don't they? Because they're suggesting that there are inherent processes that come from the brain that are applied to provide the organization and perception. Okay, so the structuralist, I say, is more of an empiricism. The Gestaltist, I say, is more of a nativism. And that was certainly something that was discussed back in their time, too. And the Gestaltists took issue with that. They really didn't like the idea of there being perceptual knowledge given at birth, or that, that there was some sort of kind of representational system, some sort of processing skill that people are born with to do this. They said that what we're talking about here, the basis of the brain's functioning to allow for perception, doesn't have to do with inborn knowledge. It has to do with the laws of nature. We're just applying, the same sort of field dynamics to the brain as our friends down the hall, the physicists down the hall, are applying to, inanimate sorts of systems. And so the reason I have the planets there, the planets, is to them, and I can't remember who has this quote. It's one of the Gestaltists. To say that the perceiver is born with the knowledge of how to organize a stimulus is like saying the planets know how to revolve around the sun. An apple knows, it has the knowledge, it has the mental process to fall to earth. So that makes no sense, right? Why do we need to kind of apply, information processing, mental representation in the psychological case, but not in these other physical cases that are working along the same exact physical principles as what we're trying to explain? So they were very, very careful about this. I think, when you learn about this in an intro class or, in classes that don't really concentrate on this subtlety, it's nativism. You're born with the ability to do it. You're born with the knowledge you need to do this. And they're saying, no, we are a brain that is part of the physical world that has the same sort of physical principles applied to it, including field dynamics. And so saying that we are born with the knowledge to organize stimulus is like saying the planets are created with the knowledge they need to keep circling the sun. Or an apple is born, it grows with its knowledge. There's some sort of internal representation, some sort of internal mental process it needs to fall on Newton's head. Say, no, let's not do this. And this is really great. So you're wondering, okay, we're going through a lot of history here. Why do we really need to spend so much time? And I completely understand, this part of this course is to go through perceptual psychology and its history and cognitive psychology. We have to go through some of this. But let's pull out something really cool here. In the very beginning, we said psychology is a special science. We talked about the fact that unlike the other sciences, there seems to be something, extra here. There's something by kind of including a mental process. There's something the other sciences don't have to really deal with. Here's a move by the Gestalt to say, yeah, look at what we can do here. We can kind of pull back from the mental. We can pull back from having this kind of extra stuff, the ghost in the machine, all this, and explain perceptual phenomena as it exists in the same natural world as we explain physical phenomena. And that's a really cool move, and it's something I think we're going to want to kind of come back to and see if we're, are there ways we can do a psychology without this, this kind of mental placeholder that we kind of assume as we go through it. I mean, so yeah, it's old, but in some ways it's really provocative and I think very modern. Okay. So is Gestalt a nativism? And they would say, absolutely not. It's not a nativism in the sense of how Locke would have, or even Kant would have portrayed nativism. It's not as if we're born with knowledge, born with a process. Again, it's just part of the physical world. And so here, what we're going to do is kind of address different types of reductionism, scientific reductionism, just very kind of superficially. I believe one of your readings does this in more detail if you're interested in it. But you have a sense of what reductionism is scientifically, right? I mean, this is something that I maybe you've had to deal with just with your friends that aren't in psychology, or maybe even your friends that are in kind of wet lab neuroscience or something like that. And you've probably thought of it too, that when it comes to explaining things from the perspective of psychology, deep down we know that, well, that's good for the psychological level of nature, but ultimately those are going to be explained by biology, right? So maybe we're getting closer to an absolute truth and potentially the predictive power of science if we can show that whatever we're talking about psychologically is in fact reducible to neuroscience, right? So, even the fancy pants stuff, like our social interactions with people, yeah, when it comes down to it, those are really neurophysiological processes, and that's where we're really going to find the truth. And then, the chemists down the hall, or we can go, I guess, now from the neuroscientist to the cell biologist, say, yeah, really your answer is going to be more in the cellular workings of what's going on. And the chemists down the hall are then going to say, well, if you really want to know what's going on with the cells, you really kind of need to look at the chemistry. And then you go down even further down the hall, and the physicist says, well, that the true level, the most fundamental level of explanation is going to come from my department, me and my friends. It's physics. And, we there's kind of an assumption about this, and we can go the other way too, by the way. We can go, well, sociological phenomena, political phenomena, all those sort of things that are way up there, can be reduced to psychology before we kind of then fall all the way down to physics. But this is reductionism, right? That yes, you can do psychological research or you can do neuroscience, but we know deep down this is in some ways giving a job description for the biologist, the chemist, and the physics to get to the real truth. Because boy, when you get down to the level of physics, you can, determine everything and make absolutely precise predictions. Now that's a very kind of classical way of thinking of it, right? But we do have some assumption that physics is the privilege level. It's the level of description that is going to be most thorough and is going to be the one that's going to really reveal the laws that we're after, the laws of physics, the ones that are really, really predictive and thorough, and that's where the true reality lies when it comes to it. And yeah, we're getting paid to be, neuroscience, cognitive neuroscience scientists and all that sort of stuff. And it helps, and there's, tons of applications and all that sort of stuff. But ultimately, maybe next year when we go back, the physicists are going to say, oh, we can solve all these problems now. No, it's not going to be next year. But, it's kind of something in the back of our head, right? And it's, talk to the folks in social psychology, and they'll say, yeah, we know we can kind of reduce things down to cognition, and then you folks can reduce things down to the neuroscience and all that sort of stuff. It is kind of a big assumption that's in the back of our heads, and it does play a role so psychology. It does play a role. What I was going to say is it plays a role in the politics of universities sometimes, right? So you might notice that in our university, much to the dismay of some of us, has psychology in the humanities, right? Not psychology in the CNAS, the science part of the university. And the department has discussed that. There's practical reasons we have stayed in this college. Some nice practical reasons. I mean, the fact that you're able to get TA-ships through your 5 years probably is something that benefits us being in the College of Humanities. But we feel that there is also, we probably have more to discuss with the folks in the sciences than we do in the humanities. And not to say, there aren't wonderful, smart people in the humanities, but, it's kind of weird that psychology, especially given its kind of continuing shift towards kind of neuroscientific bases, that we're still in the humanities, right? So, I mean, that's just something that kind of plays into this kind of old reductionist or classic reductionist sort of perspective. But there are other perspectives on this. Again, this comes out of the connection between psychology and natural law. And there's something called new reductionism, which is now about 20 years old or so. But it's still kind of, I've seen it kind of raise its head with other terminology. Consilience is a term I've seen, but it's the same idea. And it's this, that there aren't any privileged levels of nature, that psychology, biology, chemistry, and physics all look at different levels, but they are not really reducible to each other. You can find correspondences, right? Certainly you can look for correspondency. That's an important thing to do. But they are all valid, and they all have real, unreducible phenomena, right? So the questions you ask in psychology are not really placeholder questions. They are true questions that will have answers in psychology, okay, including neuroscience, that yes, you can find correspondences for in biology, chemistry, and physics, but the place to look for the answers is psychology, and those phenomena are as real as the phenomena in physics. But there is a reduction that can be made. All four of these sciences, and we can go in the other direction too, including sociology, poli-sci, and all that stuff, reduce to a small set of physical strategies. In other words, and I should mention, some of these physical strategies are going to be borrowed from physics because physics does reveal these strategies maybe more readily than the other sciences. But those strategies are as applicable to psychology, biology, and chemistry without there being a reduction between these different sciences. So things like the conservational principles, so conservation of momentum, mass, all that sort of stuff, of charge. People have tried to apply those in each of those different scientific contexts. Statistical mechanics has been applied to physics and chemistry and biology and psychology. We're going to see more of this as we go on. Kind of order out of chaos systems. What else? Certainly you find folks even higher than psychology, sociology, poli-sci, applying kind of connectionist dynamic systems to what they're looking at. And this is a style of science that some people think is probably healthier than the old reductionism perspective. So yeah, self-organization. I have this down too. Self-organization is a principle that it will see in physical examples, physicists' examples, but you also see in all the other sciences. And to try to find kind of a small group of generalized principles and how they appear in each of the sciences is a really kind of provocative way of going about it. And some of the first folks to do this when it came to understanding psychological phenomena were our friends, the Gestaltists, right? And so I would say that the Gestaltists, even though it certainly predated the term new reductionism and the term consilience, and a lot of the approaches that the modern neuroscience and biology is taking, they really were, kind of these new reductionists, and they were applying their explanation of brain states by borrowing a very, very fundamental physical principle from physics and applying it to psychology, taking field theory dynamics and saying, wow, this is so successful for physics. It's much more predictive. It's an elegant explanation to describe what's going on in these complex systems, apply field theory to it. Let's just do the same thing in psychology and see if we can do it. And they say, geez, a Gestalt's a great way to do this, because what we can do is consider all these laws of organization that we've been discussing as kind of perceptual moves towards stability. Whether we're talking about, the law of simplicity, the law of proximity, closure, good continuation, these are all part of this kind of overarching law of simplicity. Like, remember the law of prognons, I think we called it. And that overarching principle, that perception moves towards simplicity, perception moves towards stability, is really very reminiscent of what's going on in physics with field theory. So maybe what's going on is we're dealing with a brain that is kind of engendering the same sort of physical dynamics that's going on in physical fields. So it is kind of a cool way of thinking of it. It was a very cool way of thinking of it then, and it's a way that I think is again coming back, which is interesting. Okay, let's see, what else do I have here? Okay, let me just take a second here and see if there's any questions. Anyone have any questions? I didn't lose you, did I? Everyone's been so quiet, which is fine. I just want to, you're all here. There you are, hi. I just talked a lot. Does anybody have any questions on this part or anything like that? It's okay if you don't. Just wanted to make sure you're all, yeah.
So for the reductionism, like, I'm still wondering, like, how to express the point of these kind of theories. It's like, for reductionism, for people that believe in reductionism, they just can state that psychology are physical strategies, or like psychology is formed by physical strategies or something like that.
You're talking about new reductionism, is that correct? Not classic reductionism.
Yeah, maybe, but I mean, how do we express that kind of error?
Yeah. Okay. So yeah, I understand that it's kind of a little bit of a tricky thing, right? So in order to get to the true laws of nature, according to classical reductionism, psychological phenomena would need to be reduced to biological, then be reduced to chemical, and then be reduced to physics. And only at the physical level of analysis can you find laws that are real, okay? New reductionism says those laws, those physical principles, can actually be, borrowed from physics and applied to each of the sciences directly. and they're not really, I mean, they are generalized principles, but it's not like physics is the only level of nature where you would see them. It's just that physics is often the place where they're most easily seen, but they also exist in psychology, biology, chemistry, and on and on. It's just that, sometimes you have to wait a little longer. You have to understand more about the complexity, since each of these different levels kind of deal with kind of more and more complex systems. They're not as readily seen there, but they are just as real there. And the psychological level of nature is a real level of nature. It absolutely exists. It's not reducible to anything except the same physical principles that apply to biology, chemistry, and physics. Do you understand what I'm saying? So what the new reductionists are saying is that physics is not a privileged level. That is not the only level where you'll find, laws and real explanation. Where the old reductionists would say that, new reductionists are not saying that.
So for the physical strategies, maybe we're talking about something like the field theory.
Yeah.
Right.
Yeah.
But I mean, in a psychological world,
yes.
When we are talking about field theory, maybe we're not talking about the original version of the field theory, right? Because we are not assuming that there is a kind of a real field in our brain or in our mental world.
But let's just, okay, so let's put on our Gestaltist wigs right now. And not, we've been, certainly we've had ingrained in us that, the brain is much more than that we're going to lose properties of the brain and kind of the cellular by cell, the cell by cell sort of kind of computation that goes on in the brain, if we think of it like that. But the move to do that, so what you're saying is they're being naive, they just didn't have the right tools. But if you take that approach, it is a new reductionist approach. And we're going to see later on that there are neuroscientists who do take a much more molar approach, to the neuroscience than what you're typically trained on. So the move is a new reductionist move. I know you're thinking that's kind of, quaint to think of the brain as a field, right? That seems antiquated now. But the move to do that is, and you're going to see that there are other examples of that are much more contemporary and much more grounded in, the sort of, empirical science that occurs, right? So even though it seems old, kind of seems that's, kind of naive in some ways right now, it might not as we go through more modern, very, very modern theories. Okay.
Yeah, I mean, the logic here, the logic of field theory is modern, and that like what the computational neuroscience is doing, right? Like the attractor dynamics, it's really similar to field theory.
Yeah, absolutely. Yeah, that's exactly right. Yeah, good. Yeah, no, you know where we're going, right? You know where we're going, right? So
yeah.
But go ahead.
But I'm just like thinking of like for the attractor dynamics or something like that. They are based on like neurons, like discrete things. But the the method of reaching stability is through the interactions between neurons, right?
Right.
But for the field theory, it's talking about the interaction through field.
Yeah.
But it's not through like axils or something like that.
So I agree. Yeah. So this idea of that there's there's some sort of pattern formed in the brain that's like a stable triangle or something like that. I think that is very naive, right? I mean, it's not so, but there are aspects of it, and I think you're absolutely talking about it, or linking up of different regions of the brain with oscillations and things like that. All that stuff is just the move to make kind of a more macroscopic description of the important processes of the brain is in some ways a new reductionist sort of approach to it. Yeah.
If you think about like the levels of technology that we had like now and then, back then they couldn't really detect differences between like individual neurons. They couldn't necessarily understand the architecture. So it does make more sense to kind of abstract it a little bit out into the field where you don't necessarily need to detect like the individual changes, just the changes in end states.
Right, absolutely.
Right?
So I mean, I'm being very kind to them in some ways. Certainly, the theory was partly based on the constraints of the technology. Yeah, you're absolutely right by that. But I don't want to lose the kind of the idea of this, because I think it comes up again in modern neuroscience. So yes, the technology is rudimentary, and that kind of said, well, we can't look at individual cells very well, so let's ignore them and look at the big properties. I think it was more than that. I think that they were really trying to, kind of apply physical principles to the brain in a way that had not been done before. We're going to see this tension throughout our discussion between kind of the kind of structural and the kind of holistic, between the molecular and the molar and that sort of stuff, in understanding both the brain and understanding mental process. But it's good to kind of maybe take some pieces, even if I'm gonna go through a little a set of slides on the criticism of Gestalt, and I'll tell you what happened historically and everything. But if we can take pieces from each of these theories and say, geez, these are still things that are appearing. And I think this is one of the most provocative things that Gestalt has had to offer that I think still plays a role in modern cognitive science. Okay, no, great questions though. I think you guys are really thinking. That's wonderful. Anything else?
I have something. Is it, and this is going to be a real stretch, I feel like, but is it safe to kind of like draw parallels between their conception of this field theory idea and something like culture?
Yeah, culture. Is that what you said?
Yeah.
Yeah. Oh, absolutely. Yeah. I mean, you can find. I mean, I remember. God, I took one. I think I had a graduate course breadth requirement. I took something in family dynamics, which I didn't know anything about. It's the only clinical course I ever took. No, as an undergraduate, I remember now. And yeah, there are. I mean, back then they were popular. I don't know if they're popular anymore, but kind of dynamical systems approaches to social systems, like family dynamics. That you can think of the family as a field, and if one of its members kind of strays, it adds a potential, and the whole family needs to kind of reconfigure and find its dynamics. So even on that level, yeah. And then certainly culturally and politically and all those sort of things can borrow from the other sciences. So here's the question for you. I mean, you're going to see this in other contexts. Is it just metaphor when that happens, right? Is it a useful metaphor to think of a family, to think of a small culture as having field dynamics? That, yeah, it's kind of fun. It kind of works like paper clips and magnets and stuff like that. It's a nice metaphor. Or is it a true kind of observation of another system like this? And it's probably both. I mean, in some ways it can, it's hard to determine whether you're just kind of applying a metaphor or seeing a new kind of instantiation of a true physical law at a higher level. It's not easy to determine that.
Yeah. So with that being said, is it possible that this is a construction that humans have come up with, similar to something like religion?
So are you asking whether new reductionism is like religion, or are you asking, is religion a field property or something like that? The former or the latter?
I guess more like, so we've come up with this field theory, which is based very strongly in the physics that support it, but then to apply that kind of idea to culture and this, it kind of reminds me of like, okay, well, what if we are putting our own bias on this thought just to make ourselves feel good?
Yeah, no, absolutely. And that's the thing. I'm glad you're thinking about that. And I think the best way, I don't have an answer for you right now with regard to this perspective, but I think it is just something that you should be contemplating, just like you are. And yeah, think about it. I mean, I wouldn't say that is it like religion, in that we're kind of imparting our own kind of biases and trying to maybe justify that there's truly a psychological level of analysis. I think we're going to see other examples where it might seem that, boy, this can be a productive way to do it. But yeah, we have to be very wary of this. We absolutely do. You often see, this sort of move made in contexts where it seems like it hasn't been thoroughly kind of considered. Say, oh, cool, physicists are doing this now. Let's see if this can apply to political systems, that sort of thing. It has to be kind of considered thoroughly in order for it to really be a useful scientific move, I think. So yeah, it's a great question. All great questions. Okay, anything else? Okay, I just thought I would kind of take that little kind of detour there, but let's continue. And I wanted just to talk about one more principle here of the Gestaltists that I think will be useful for us later on. And this is now from Kafka. So we've talked about Ehrenfels, Wertheimer, Kohler, and Kafka. And again, I'm not a names guy. And the older I get, the fewer names I remember. But you should know that if I say what are Kohler's 3 questions, you should remember or three possible answers to the question of why do things look like they do. You'll say, oh, Kohler had these ideas, but I'm never going to ask you who had these 3 possible answers. Was it Kafka or Kohler or something like that? You should just recognize the names. Kafka came up with this idea. The idea that there are essentially, this is going right back to perception now. We're kind of turning away from that kind of physical perspective now and talking about there being 2 environments in which we can describe perception and the animal's behavior. Okay, one is what he called the geographical environment. And we're going to see these concepts. In fact, we have seen these concepts before, but this is how the Gestaltists talked about them. This is how your readings will talk about them. The geographical environment is essentially the environment of the physics, of the external, objective, non-mental world. So it's the physical world that the animal is interacting with. And these things are, again, just measurable by the tools of physics. We describe these things in their most, quote, objective terms. So they are animal neutral, right? And they're meaningless. There's nothing inherently meaningful in the things that are in front of you right now in your rooms. Any sort of meaning must be given, by the animals somehow. They are animal neutral objects. And we typically think that the description of the geographical world, the physical world, is most accurately given as molecular sort of descriptors. Okay. Versus the behavioral world, which is the world that the animal interacts with that is going to be relevant to the psychology directly. So this is a mental world. This is animal referential objects with meaning. And typically, we describe these things using more generalized or molar sorts of descriptors. So the animal can be thought as both interacting with the geographical world and behavioral world simultaneously. It's just which type of description are we going to give that environment, okay? We have seen this before. We've seen it before in the context of the incommensurability of natural kinds. Remember, there's the world that physics describes. It's the objective world. It has nothing to do with our desires, our intents, our apprehension of meaning and stuff like that. But in some ways, the animal is interacting with the world in a way that seems based on some sort of mental representation, in a way that seems meaningful, and in a way that seems that the objects are meaningfully approached with animal referential, animal relevant sorts of properties. So I'm trying to think, okay, my cell phone, it's great. It's the most important thing in my immediate environment, right? We can describe this physically and measure it and, do a engineering analysis and all that sort of stuff on it. That's fine. And that's an objective measure. But the one I'm interacting with, and when it comes to the mental world, is my ability to interpret the things I see on this, okay, are in fact based on my mental representation. These are meaningful things. And usually we give this a more molar, meaning a more kind of general, kind of higher level description. Maybe you can even say a psychological versus a physical description or something like that. And Kafka said, this is an issue. I mean, this is kind of the mind matter issue, right? This is what we've been discussing with the meaning seems to be this kind of piece of the machine that kind of gunks things up. Other sciences don't have to deal with this. How do we, reconcile these things? And what Kafka said was this. They say, well, Gestalt actually makes some headway on this. Gestalt actually begins to address this mind-matter sort of dualism. Because when it comes to how the matter is described, how the geographical environment is described with reference to the brain, molar descriptions can be applied there. So what they're doing is they're saying they're going to apply a more macroscopic sort of description to brain processes in the form of these fields. And in fact, it allows there to be this isomorphism between the brain processes and the perceptual experience. This is just a little review from a couple of slides ago, right? And so the fact that we're able to have a percept that has the property of stability, that has the property of equilibrium, is because the brain has those properties. And what we're doing here is we're applying the same kind of molar macroscopic descriptions to what's going on in the brain and what's going on in the mental process. So there we have a reconciliation. So, it's like, you can cross out up here, say, well, this geographical environment, when it comes to the brain, which is a material thing, it can be molecular, but it also can be molar. And maybe, as the Gestaltists suggest, the molar properties of the brain are the ones that are the most important. And so there's a bit of a reconciliation here. We don't have to talk about these two environments as completely distinct, because both can have molar descriptions, okay? But that being said, he was very, very aware of there still being this dichotomy, this kind of duality between the geographical and behavioral. So no matter what we do here, when it comes to applying fields to the brain and to perception, to the neurophysiological dynamics and the basis of these perceptual organizational principles going between these two worlds, between these two environments, still leaves the problem of meaning. How is a molar description of the neuroscience, of the neurophysiology, going to allow us to explain meaning? Somehow that's coming out of the behavioral environment and not the geographical environment. And he gives the kind of very intuitive example. So where does meaning come from? So even if we can give a common set of descriptors to the material and the mental, we're still left with the problem of meaning. And he gives this great example of the phenomenal mailbox. Well, it's a little dated now, as it turns out. But, there's a mailbox there. Actually, the mailbox probably, back then, that is how most people mailed letters. They would have a mailbox in front of their house, and to let the postman know that it was time to mail a letter, they'd put their little flag up. I don't know if you even have mailboxes at your home. I don't know if people use those anymore. And if you have little flags, we do in fact have a little flag on our mailbox, but the nature of the mail system is that now we never allow mail to be sent using our own mailbox. We go down to the mailbox down on the corner, the big one that seems to also becoming less and less common. In fact, I got a little anecdote. When my kids were younger, my older son in particular, I think when he was about 10, I said, no, maybe younger than that, like 7, 8 or something like that. And we stopped at the mailbox and I said, can you mail this letter for me? It'd be fun. And he went up to the mailbox with the letter and he had no idea how it worked. He says, how does it take it from me? He said. So I had to get out of the car and show him, And actually, I don't even know if they have the handle pull ones anymore. But anyway, that's a little aside. What Kafka wanted us to realize is that the physical mailbox, imagine the big blue ones I'm talking about now, the physical mailbox had no inherent meaning. It only had meaning when a person had the intent to mail a letter. Okay, so the person's intent provided the animal referential characteristic of that object. So it has to be the animal that's applying meaning. So this dual environment, yes, it can be addressed a little bit. It can be reconciled a little bit based on the kind of common molar descriptions to the brain and the perceptual organization. But it still leaves the problem of meaning. And what Kohler's saying is that a mailbox doesn't mean anything unless a perceiver has the intention to use it a certain way. Okay, so yes, that is still this dichotomy that cannot be solved with their kind of molar sort of approach. We're going to see later on in the class a perspective that suggests that a mailbox always provides the meaning of mailing a letter. Okay, but we'll just leave this here for now, but realize that even as far-fetched as it sounds right now, meaning can be seen as inherent in the geographical environment. Okay, but for now, we'll just leave this here. So this is a way of setting up a discussion later on. Okay, let's move on then and go through some of the classic criticisms of the Gestalt approach. Now, I can't remember if I said this. I think I did say this last class, that these days you don't find a whole lot of kind of pure Gestaltist explanations for kind of the core phenomena of vision. Where I see it, I think I mentioned I see it in music perception, certainly. I mean, it is probably one of the most used sets of explanations in music perception. It's also used, it's used in the psychology of magic. I'll see. I teach an undergraduate course in the psychology of magic. And when it comes to things like, the sawing a lady in half or apparently cutting a rope, but not really cutting the rope, all that sort of stuff. Very often explanations will borrow from the Gestalt approach. But when it comes to kind of the deep explanations, I don't think there are many folks that kind of follow a strict Gestaltist sort of approach. That doesn't mean that parts of it haven't kind of been translated, as I said. We'll see that later. But I need to go through the criticisms and what historically led people to turn away from the approach. So back then, a lot of people had concerns about the methodology. Wait, does this work? No. Okay. You remember this? Oh, shoot, I don't think this works. Yeah, it doesn't work right now. But remember this one. This is the one with the ball going back and forth. Remember that people criticized the methodology of the structuralists, right? They said it was too introspective. The Gestaltists were critical of that as well. But what they continued to do is basically ask people what their perceptual experience was. They didn't really use, at least initially, much of a more objective psychophysical sort of approach. So they would sit people down like Wertheimer did and show them the phi phenomenon, which is why that ball is supposed to be moving there, and ask them what they perceived. So it was a very straightforward sort of methodology. What's perceived? And people would say, oh, I see a bar moving up and down. I see a ball moving back and forth, that sort of thing. And so people took issue with that, kind of the kind of open-ended approach to the methodology. Now, clearly that can be, that has been corrected with more kind of common psychophysical and neurophysiological measurement techniques. But that was one of the criticisms. Another, probably more potent one, was a criticism of the Gestalt laws. The Gestaltists were actually more careful than they're commonly given credit for. But back then, people said, what does it mean for things to be proximate, for elements of an image to be proximate? What does it mean for elements of an image to be similar? Or, what does closure depend on? And the Gestaltists, to their credit, did try to mathematically establish what was critical for proximity to kind of organize the perception, what was critically important for similarity in the element structure to work. They tried, I mean, they knew that was something they were going to have to do. They were not dumb guys. They say, well, proximity works when things are close together and that's all you need to know about it. No, they wanted to objectively determine what constituted proximity in image elements. But that's not how, that was something that was kind of coming later, and a lot of people took issue with this. Along with that is the notion that the postulates, the explanations, are in some ways, they seem to be rephrased problems. Okay, and what I mean by this, the problems become postulates, is that the law of prognons is a great example of this. So why do the laws of why do the organizational laws work? Well, you and I know that it had something to do with the brain science, according to Gestaltists. But initially, at least, they said, well, it's because the perception is always going to move towards simplicity. Perception is going to move towards the simplest organization. And a lot of folks felt that was not a sufficient explanation. It's like, okay, so perception moves towards organization because perception moves towards equilibrium, which is going to be organized. So at least on a first pass, it kind of sounds like it's a rephrasing of the thing they're trying to explain. And that's what I mean here by problems becoming postulates. They're just, it's something that I think that all psychology has to be very, very careful of. I mean, in a very superficial way, you can say, how do you explain the fact that I can remember what my second grade teacher looks like? Okay, I loved my second grade teacher. She was one of the best teachers I've had. No longer with us, I'm sure, but she was old then. But I have a good memory of her. I think I know Mrs. Downs. I think I know her. Why am I remembering that? And a kind of initial explanation could be, well, that information is in your long-term memory, and that's how you're able to do it. You can retrieve it from your long-term memory. There is the explanation of how I just remembered my second grade teacher. That's another kind of very kind of circular kind of problems becoming postulates sort of explanation, right? I mean, we know that we've got to do more than that in our explanation, but we've got to be careful of this type of thing sometimes. We don't. It's not that we can remembering something just because the information is in our memory is not a sufficient explanation. Things being perceived in their simplest configuration because of the principle of simple configuration is not going to explain it as well. And it's a problem, for all of psychology. It's possibly a problem in social psychology sometimes. Dissonance reduction. Why do we try to kind of make our explanations or understanding something that is consistent with our beliefs? Well, as dissonance reduction accounts for that. I mean, it doesn't really account for that. It describes it. It's kind of a descriptive term for the thing we're trying to explain. So we always have to be careful of that type of thing. It was felt at the time that the Gestaltists weren't careful enough, that there was too much of that kind of circular explanation going on. And then, a lot of people didn't think that the neurophysiological explanation, this field theory idea, was really sufficient either. It wasn't satisfying because you could, as it turns out, do a lot to the brain that might, in fact, disrupt the field dynamics without disrupting the perception. And so a lot of folks felt this was neurophysiologically untenable. You can look at the readings on the different experiments that were done, I think, with animals. Pretty much all of these were done with animals, where the Gestaltists at the time had kind of discuss the importance of the electrochemical aspects of the brain dynamics that certainly should be disrupted if you put things that would disrupt an electrical field in, like, pieces of foil. If you put that into the brain, that should absolutely disrupt the electrical, field dynamics. But the animal would be shown through conditioning techniques to not have a changed perception, even though the dynamics of the brain seem to be so obviously disrupted with, placing, like little foil pieces of metal pieces in the brain where it should be disrupted. So a lot of folks found their neurophysiological unsatisfying, and I think you folks did, which is fine. It in some ways it is a little naive, right? Again, we do kind of, I think we can take some things from their approach overall, but yeah, it's naive and certainly constrained by the technology of the time, absolutely. And I think that people were easily able to show that, it can't be something so simple as just electrochemical dynamics, because we can disrupt those dynamics and still show the animals perceiving just fine. So all those things were criticisms of the Gestalt approach. But probably the reason people most turned from the Gestalt approach at that time, and now we're talking about the 30s, 40s, 50s, is because of two things that happened. One is, you probably know of this work, of course, new neurophysiological evidence that there are detectors in the brain that seem to respond to those atomisms, and specific atomisms that our old friend Wundt was talking about. Okay, cells in the brain that respond to just horizontal lines, or just angled slanted lines, or just horizontal, right? Horizontal lines or angled lines or vertical lines, okay? And supposedly nothing else, right? Those look like detectors of, these elements that Wundt was always talking about. So when you look at a chair, your sensory experience isn't of the chair. That's a perceptual experience. Your sensory experience should be of these little lines that are intersecting and going at different angles and all that sort of thing, right? And if we can find cells, if we can find evidence for cells that are in fact detecting these individual elements, man, that would be pretty strong evidence for a brain that is looking for very specific atomisms, very specific sensory elements, right? Remember, that's something Wundt had said from the beginning. The sensory elements are critical. That's what's going to be built up into the percept, where the Gestalt has said, nah, the sensory elements aren't really that important at all. They can be interchanged and we still get the overall perceptual experience. Here we have evidence for these atomisms, it would seem. And the other thing, of course, is the computer revolution. And there is a computer that I actually, well, I don't know if I actually worked on that, but it is exactly like the one I worked on when I first started my my computer experience as an undergraduate. It wasn't back in the 1940s or 50s, of course. It was in the 70s. That's what you're looking at now, a computer probably from the early 70s. I worked on it in the late 70s. At the time, yeah, it couldn't do much. With the computer you're looking at right there probably does, oh, I know it does substantially less than one of the apps on your phone. I mean, there's, the computer that I worked on most was in when I was a graduate student, and it analyzed speech. And you have an app that can do that much better on your phone than this machine ever could do. And this machine, just to because I like reminiscing about it, got so hot that it was on a kind of separated floor, so there could be fans underneath. I mean, you go into this room and it would be the noisiest thing because there was so much air that had to be passed around. We didn't program on screens. We programmed on punch cards, which is what you're seeing right there. Okay. But even before this, and you've probably seen pictures of, kind of older kind of computational machines, and they're very charming. It was clear that a lot of what we thought of as things like mental process kind of algorithms that could be used to explain things like, size perception, distance perception, could be replicated on computational machines. And those machines, of course, worked based on, strings of atomisms, strings of zeros and ones, strings of on-off electrical or magnetic states. And so the atomisms are what allowed the perceptual process to be built up in these machines, perceptual process meaning things like a perceptual process. And if computers can do things like that, then maybe this is the way to understand mental process. So there was a shift then back to structuralism in a way. You'll see it's much more sophisticated than structuralism, of course, but it really was one of the main things that led people to kind of reject the Gestaltist notion that the atomisms are overvalued. Here we have evidence that the brain loves atomisms. It's designed around atomisms, and computers show us that atomisms can be wholly effective to do cognitive or psychological like things, which leads to our next approach historically to perception, which is going to be the computational approach. But I think this is probably a good place to take our little break before we get into that. Are there any questions before we break, or you want to take a break and then come back and see if there's questions? Looks like Morgan already is on her break. So why don't we'll take a break, 10-minute break, and then we'll come back and I'll answer any questions and we'll start the computational approach. Okay? Okay.
Sounds good.
See you in 10 minutes. Hello. I think we're working. Is that 10 minutes?
Yeah, hey Larry, can you see me when I turn my camera on? Because I only see black.
Ooh, I do not see you. Do you have your lens opened?
I don't have anything on.
You don't have anything on it?
I might leave and rejoin real fast.
Okay, go ahead. I won't. I'll give it a minute or so before I start. Mac, I got your message. That's your chat. It looks great. I understand. I'm glad that you made that connection. That's nice. I wasn't aware of that. That's great. All right, there you are. Great, thank you. All right. So I think we can start. Michael, you're there? Well, recording. Hey, you guys been using the recordings at all? I didn't check to see if people have been watching them. Have you? I mean, I should continue to make them, right? It's good to have them there when you want to study and stuff. Yeah. Okay. Good. I'll continue to make them.
Yeah, I honestly haven't looked at one yet, but I do intend on it.
Okay. No, I won't take it personally. You know, it's funny. You can monitor them after you put them up on YouTube to see how many people watch them. And for my undergraduate class, you know, I get like 250 people in the class, and nobody watches any of them until the like 2 days before the midterm, and then it was like that. It's like, oh gosh, that's not a good way to study. So I know you folks know better than that, but okay. Any questions from the stuff we went through last before we get into this computational approach? Yeah. Okay. No problem. If anything comes up, you just let me know. Let me now.
You know, I just thought of something.
Go ahead.
Can you give an example of the difference between molecular and molar in terms of like brain stuff?
Sure.
Or like psychological concepts.
Sure. Well, what the Gestalt is meant by it is that you know, like the physical world would be described by things that were very small. That's really where the physical kind of, you know, the important physical stuff lay. Where you really couldn't get down to that very easily when it talked about behavior. I mean, you know, you can talk about strings of reflexes and things like that, but that's still at a much more kind of molar scale, and being that these are much bigger things. You know, the things that are analyzed, the things that are considered relevant at those two levels are typically thought about as being, you know, kind of much more generalized versus much more kind of, you know, we're talking about, you know, parts of the atoms and things like that that are the physical things, in other words. Where things that are more behavioral are necessarily described as being, you know, larger. So molar here would be large, molecular would be small, and that's kind of the only kind of important dichotomy. What they thought, of course, though, is what I said at the last slide, is that Kafka thought that by actually describing something that was physical in the geographical world as molar, which would be the brain, the neurophysiology of the brain, which is a material thing. Applying field theory to that is giving it a molar description. And here we have this isomorphism now between a way of describing the geographical environment with kind of, you know, larger units, and the behavioral environment, again, with larger units. And these two things can be compatible. In fact, they're so compatible that they're isomorphic to each other. So he found that a way of making progress on trying to rationalize these two types of environments that you can use to describe where an animal is behaving. Okay? Does that help? Yeah? Okay. All right. Then let's go ahead and start talking about the computational approach. Yeah, see, this is the thing. You folks aren't teaching, but no, I don't know. Did we have trouble hearing sound last time I showed a movie? I can't remember. Now I figured out how to do it. You have to click when you share screen. It didn't used to be like that. When you teach, you'll have to worry about these things. Don't worry about it now. All right, anyway. So hopefully you're going to be able to hear things. Let me just ask if there's some audio demonstrations in this. If I do this, Can you hear that sound? Let me look at you. Hold on. Can you hear me go tick? Yeah, good. Okay, it should work fine then. All right, here we go. All right. So, oops, let me go back here. So we're going to talk about the computational approach, and we're going to call this theory 3. I'm a little loose with what constitutes an actual theory, but it doesn't matter. I mean, you know, you should be able to understand the distinctions between a computational approach and Gestalt approach and structuralism. And clearly, as I suggested before, in moving back towards atomisms, we are going in some ways back to structuralism, but we're going to make it a more sophisticated take on it. The atomisms are going to be central again, but the way the atomisms connect, the way they are structured is going to be much more sophisticated. And so if you look back in some of the readings that describe kind of the evolution of the computational approach, sometimes it's called constructivism, which is kind of a kind of a takeoff on structuralism. Constructivism is going to be just that the atomisms are put together in highly sophisticated ways, not just association, to give rise to the kind of the holistic perceptual experience, or the cognitive process, or the psychological sort of experience. Other times this is called information processing, which is a term, that's the term probably you will continue to see through modern psychology and cognitive science, information processing. Back then, we also called it the artificial intelligence approach. Artificial intelligence has, I think, appropriately has now known as something much more specific than that. Trying to get computers to act like they have intelligence. And then there are all the kind of interesting philosophical questions that are around that. But back then, we used the term to try to borrow computer processing to see if, in fact, that's how animal and human mental processes might have worked. So you might see that term in your reading artificial intelligence. Know that it meant something a little different. It meant something in addition to how we currently use the term now. Back then, it was also used, as I said, to see if you could model mental processing on a computer, not to get it to have sentience or consciousness and take over the world, nothing like that. But can we then use that modeling to explain mental phenomena? The purpose was to explain mental phenomena. So it was a cognitive science sort of term. Okay. In all these cases, we're talking about the same thing, and we are talking about a general principle that is still very much relevant to psychology. And that is the notion that computations in the mental process are made on representations. Okay? And it is something we saw earlier with regard to unconscious inference. So we're kind of taking ideas from the beginning of our discussion of the history and the inference making process that is part of the history of cognitive science, and bringing it up now to a more modern version in the 60s and 70s, this computational approach, where in all cases we're talking about there being representations of things in the world given through sensation, and then elaborate kind of manipulations of those representations. Computations being manipulations of representations. And computation here will be borrowed from computer science, of course, but the same idea is kind of core to all of these approaches, that some manipulation of mental representations are conducted by the brain in order for us to have mental experience, in order for us to have psychological contact with the world. And that is, that's very general. I mean, you can probably use that phrase, computations or manipulations of mental representation, to describe almost any theory of psychology, right? So let's make sure we're aware of that, that even though we're talking about something historic, we are talking about an explanation that starts with this far-reaching perspective on mental processes that carries through modern day. Manipulations are made on representation. Clearly here we're going to be borrowing mostly from computer science to discuss those manipulations. Okay, so we are clearly talking about this unconscious inference process, right? This is exactly what we saw a couple of weeks ago, maybe last week, where you go through this energy being imparted to the receptor surface, the eye, as an example. Sensations are extracted from the receptor surface, and then educated guesses are made about what the sensations are telling us about what's in front of us, and our interpretation of those sensations come from some knowledge we have, whether it's from birth or from our experience. We'll call it this memory, and that helps inform the unconscious inference made on the sensations to give rise to perception. Okay. So we are talking about, this is just another form of unconscious inference, but we're going to make it more sophisticated. We're going to try to dig into this box here to try to understand what sort of principles allow for the inference to hopefully be successful. Okay, we're going to dig into this box here. We're going to also look at how these play a role in these processes, but this is really where we're going to concentrate now. And this is a great example. I mean, this is in some ways, the first computational, I guess, example we saw of how a perceptual process might work, right? We start with these, some sensory inputs, and then we kind of make computations. We kind of go through a series of steps, and bring also with us a way of interpreting the different sorts of cues that might be there to tell us something about what else is in the image to give rise to perception. So that is, in some ways, a computational process right here. Okay, it really is. It really is nothing at its heart very different from the sort of computational explanations that will be given in this more modern example of this. Okay, so let's go way back and talk about what computation means, though, as it's borrowed from computer science. And I know this is review for a lot of you. I'll go through it quickly. I just kind of want to pull out the kind of important pieces of this so we can readdress them later when we talk about some of the philosophical implications. So I'm pretty sure most of you know of Alan Turing, right? I think that movie helped a lot for his notoriety, right? Which is not a bad movie. What is it called? The Imitation Game, right? It's not bad. It's worth seeing if you haven't seen it, with Benedict Cumberbatch. It does, deal with some of what we're going to be addressing here. But he was a brilliant guy, character, but also so, so sad that his lifestyle wasn't accepted, and it led to his arrest and suicide and all that. Such a sad story, but absolutely brilliant man, and is considered kind of the father of computation and that sort of thing. So I'm going to first kind of talk about some concepts he provided in a 1936 paper. That's how old we're talking about computation. And what he devised was kind of a thought experiment based on a concept called binary code. And binary code is just a name for a code that's comprised of a string of symbols that only need to be in one of two states. What I put down there is A and B, but it's more commonly known in computational systems as 0 and 1. But certainly we can talk about them as being on-off states in a silicon chip, or one of two representations on a magnetic tape strip or something like that. But he said that turns out to be a much more powerful sort of code than you could ever imagine. Because if in fact you can conceive of large strings of these on and off states, these A and B states, say on a piece of magnetic tape. So do I have any magnet? I was looking to see if I have any. Did your parents have cassette tapes? Do we know what we're talking about here with magnetic tape? I assume you do. The image I showed of the old-fashioned computer that I used to work on, they had big reel-to-reel tapes, and that's really what he was familiar with at the time, is kind of these larger reel-to-reel. And the magnetic tape can, record things, and it can play things. And, in the old days, we used to listen to music that way. That then became 8-tracks and cassettes. And I bet you've seen cassettes because your parents had them, right? Anyway, I can pull one out if you've never seen one. But what he thought is that if, in fact, you have a machine like a tape recorder player that could both read the code, this binary code, and write the code, it would become this all-powerful, really very impressive machine that could, in fact, make any calculation you needed to make. So imagine now, here I am, Rosenblum, the tape reader, and the tape's kind of coming through. Okay, okay, so let's see how I'm going to do this here. Okay, here we go. Let's pretend this is the tape, right? This is just a regular rope. This is the tape. And here, let's see if I can, yeah, there. If I say a magic word, oh, never mind. It's supposed to be a magic rope. It didn't work very well. Okay, so this is the tape. And on the tape, it has little sections, say, that can either be stamped magnetically with a 0 or 1, or an A and B there. And so what happens here is, as this kind of runs through the tape heads, okay, I can read it, okay, as a tape player, and just a regular tape player, I can read the string of A's and B's or 0s and 1s, and then follow directions. So I go through this now. My nose is the tape reader. Okay, okay. It says now to fast forward the tape 2 feet, okay, and stop there and write this series of 0s and 1s. And it tells me to write 1110, 11000. Okay. And then after you do that, rewind. Okay. And there's new code. There's a code here that tells me things to do. And the code can tell me to rewind, fast forward, or write new code 0 and 1. Okay. By doing just that, he was able to show, you can basically get the machine to do any sort of processing that involves an algorithm, any sort of mathematical process, okay? And the cool thing about this is, of course, that this machine starts becoming automatic, right? It starts to become a machine that can kind of, do calculations on its own. It doesn't need, once the code is there, okay, once the code is there, that will be put in by the programmer. It can, do all these amazing things: fast forward, rewind, write new code, read old code, read new code, all this sort of stuff. And by doing so, it will allow for this ultimate power to be able for it to calculate any sort of process, or to support any sort of process that can be broken into an algorithm, like the Ponzo illusion you saw before, right? Importantly, though, this is clearly what we'll call a formal system. And what I just mean here by formal is it's going to be a system that is going to use representations that don't, in fact, that kind of extract the form out of the thing that's being represented. That's why formal is used here. But it doesn't, you don't have to understand that. These are kind of, I guess, these symbols are general. They don't have to apply to any one thing. Right? They're just 0s and 1s, and those 0s and 1s can represent a number of different things. And just like, mathematics is a formal system. This is the way I teach it to my undergraduates. Mathematics is a formal system where numbers are representing anything you want them to be, right? So say I have a 250-person class, and I'm sorry, so say I have 125 people in the class. This was actually done from my undergraduate perception class. I have 125 people in the class, but I have 250 M&Ms, and I need to know how many M&Ms each person gets, so everyone's happy and not jealous of the M&M hoarder next to them, right? And that's a calculation. It can, I can determine there's two. Everyone gets two M&Ms. Congratulations, there you go. You get the green ones. Those have extra powers. Everyone gets two M&Ms, and everyone's happy. But I can use the exact same equation not to give out M&Ms, 250 M&Ms to 125 people, but say I own not 250 M&Ms, I own 250 Chihuahuas with red sweaters. Okay, everyone gets two Chihuahuas. You get a Chihuahua. You get a Chihuahua, or two Chihuahuas, right? And again, it's the same equation, right? It's the same mathematical system that's going to allow us to represent the M&Ms giving to people, or the Chihuahuas given to people. And you don't have to have the 125 represent people. It could represent pit bulls or something like that. Now, I wouldn't want to do that to the Chihuahuas. Anyway, you get the idea that what mathematics does, what a coding system does, is it basically kind of ignores the form of the actual thing that's being represented, because it can represent anything. And that's what a formal system is about, right? What is the system itself has no substance, no meaning. And in fact, that's one of its powers, says Turing, right? We can now use this coded system that he was able to show can, do all these fancy things just by reading and writing code and, following the directions on this code to calculate anything. And so he calls this an automatic formal system because it can control itself. And it's dealing with code that can represent basically anything. Okay, so that's a Turing machine, and it's a very simple concept. Obviously, it's the groundwork for a computer. But the question then is, can we consider other types of systems that can do this sort of thing as formal systems as well? So, for example, let's see what the implications are. First of all, regarding, that's what the RE means, regarding perception, can in fact a Turing system help us understand how perception might occur? And people said, yeah, absolutely. Let's think about that inference process that we came up with before that explains the Ponzo illusion, the fact that people see those two horizontal bars as the same size. Okay, the relative sizes of A and B are first taken into account, and then the proximal size is first taken into account, and then these linear perspective things. And this is basically something like an algorithm, right? This is like going, as I used this term before, it's kind of going through a series of steps to calculate a final answer. In this case, the answer has to do with a perceptual experience. Experiencing these two things is not the same size, even though the input is the same size, right? But it's still an algorithm nonetheless. So people realize that this Turing machine can help potentially explain how a perceptual process can be calculated, how an algorithm can be used in explaining a perceptual process. Okay, but maybe deeper than that, and this is where kind of some of the philosophers and some of the psychologists, the cognitive scientists that were theory folks came in and said, this is probably deeper than just that. It's cool that we can, in fact, describe almost any perceptual process as being algorithmic. But think about this. There's nothing about the Turing machine itself that requires a certain type of material substrate. And what I mean by material substrate is what the thing is made out of, right? Anything that instantiates a binary system, codes of zeros and ones, A's and B's, on and off states, anything that is made up of a code like that and can be automatic, can read itself, can write things, can follow instructions to forward and reverse and all that cool stuff. Any system that does that can be a Turing machine. So in, kind of by transitive property, any sort of binary coded system can in fact I guess, go through perceptual processes. Whether it is anything that instantiates a binary system, whether it is magnetic tape-based, like, you know, Turing envisioned it, and, you know, the first, well, maybe not the first generation, second generation of computers absolutely were, okay? And then more modern computers are silicon-based, right? And with on-off switches and in the, you know, kind of the silicon chips that are made of. Just for those of you that are fans of these sorts of things, there is a wonderful museum in Boston called the Computer Museum. Next time you're there, absolutely go out of your way to go. It's great. It provides the history of computation and talks a lot about Turing. And there you will find, oops, sorry. Okay, very quickly, you will find a Tinker Toy based one, but let me go back and talk about her. I guess my slide is different. I apologize. Clearly, where we're going here is describing the Turing machine as instantiated in carbon-based systems. I can't believe I don't remember her name. That's how impressed I am with her. Okay, the reason why she's there is because back when I made this slide, she was thought an actress that was not thought to have a lot of range. But I think she's actually better than this. I should probably replace her with, I don't know, one of the Kardashians. Anyway, carbon-based systems. And what does that mean, a carbon-based system? What we're talking about potentially, at least as they were conceived of then, is a system based on neurons that can be in on and off states. Now we know things can be more complicated than this with neurons, but back then, you know, we thought that neurons were pretty much guided by an all or none principle, right? By this action potential principle. You know, is there enough energy to fire off the neuron or not? It's either on or off. And so neurons have the potential to code for binary strings, okay? Neurons might be, in some ways, the ultimate binary coded system. And if that's the case, then by looking at how a computational system on a computer can explain things like perception or cognition or psychology, we might not be too far away from explaining how people and animals can use processes based on binary coding to reach the same ends, okay? So here it is. Here's the move, right? That Turing machine is not wedded to any specific type of material stuff. It can be on magnetic tape. It can be on silicon-based computers. It can be in neural systems, if in fact neurons can be conceived of as being on and off, as they were certainly at the time. And so this is great. We can borrow our understanding of how a computer might calculate a psychological sort of experience and know that it could very well be the way brains do it. It could very well be. There's nothing, like computers have these properties, humans have these properties. We can never fully explain what's going on with humans by looking at computers. In fact, the same, kind of core is there. They can both be considered as objects that can support binary systems and therefore automatic formal systems potentially, right? Here's the Tinker Toy-based system. I apologize for the confusion. If you go to the Computer Museum in Massachusetts, in Boston, you'll see all that great history of Turing and all this stuff. And somebody wanted to show that, in fact, you could instantiate a computer, you could create a computer that could do some fairly complex fairly complex. At the time, it was able to play tic-tac-toe, based on Tinker Toys. I don't know if you folks know what Tinker Toys are. My kids played with Tinker Toys. I kind of forced it on them. They didn't pay much attention to them, but they're these little rods and spools of wood that can be stuck together and make kind of objects. They're kind of cool if you ask me. And what they did here is they added strings and pulleys and things like that. And you can go up to it and, try to play tic-tac-toe, and you got to pull strings to represent different things. But the way that the whole apparatus is set up is as a binary kind of system, and it can calculate what it needs to do to play tic-tac-toe and at least not lose. You either come as a draw or a win, which is just kind of the point here, is that the binary aspects, the binary coding aspects, and the fact that it can read and change its binary code and do all that is all you need for a machine to calculate an algorithm, therefore a process, and it doesn't make a difference whether it's magnetic silicon, carbon, or Tinkertoy. The important part is here is that human perception can legitimately be modeled on computers. Okay, it's not just potentially, say, well, yeah, I can get a computer to do this, and it looks like perception, it looks like memory, it looks like thinking, but clearly it's not people. I mean, back then, certainly, it was thought that people are computers. People, for all intents and purposes, are computers. There's nothing in principle different from the machinery in the brain and the machinery in the same binary system of a computer. Okay, so this is what we're talking. Yes, go ahead.
Have you heard of this is a bit of an aside, I guess. Have you heard of the video game Minecraft?
Of course.
It's kind of
my kids play it.
Right.
Yeah.
There's some fun things people have done is actually built a computer inside of Minecraft using, again, these very basic response systems. And there's the project going somewhere that they're trying to simulate the entirety of the actual game Minecraft inside of Minecraft.
Oh,
so, making it recursive now.
That can't end well. I mean, at that point, the computer is going to completely take over the world. No, so what are the on-offs? They're using that kind of based on a binary system, yeah? And what are they, to the degree I know Minecraft, it's kind of like you're using bricks to build things and stuff like that. What can instantiate the binary system in that? I'm curious.
There are basically on-off switches. There's a block that has a state, and you can set it a signal that changes the state.
Oh, that's great. Oh, that's a great thing to know. Thanks. I'll look that up and I'll add it to this discussion. Thank you very much for that, Michael. That's great. All right. So, I mean, we're talking history here, so you might be thinking, oh, there's so much difference between animals and people and computers. Maybe it seems a little naive to think of us, but let's, make sure we understand this here, that there, of course, there's an evolutionary history and all that to animals and us that might play a role here. But, if we're talking about algorithms, if we assume that mental states are really based on algorithm, if we assume, even take a step back, if we assume that it's manipulations of representations, this is a way that we can start getting pretty precise about those manipulations, right? This is really, really powerful potentially. So let's kind of put ourselves in that time period a little bit and think about, wow, how exciting this is. The computer revolution is revolutionizing psychology along with the rest of the world. Okay. Let's think a little bit about this philosophically. We'll go back and forth between some of the philosophy and then some examples of this. I think it's kind of a fun way to do that. But we're going to talk a little bit about this, the philosophy about whether this works or not. So we'll address this question a number of times, but here we go. Do formal systems know? Okay. And I bet you folks, most of you folks have gone through this in one form or another. Can we say that computers understand? Think about this. I think the algorithms that underlie Spotify, I use Spotify, the music that Spotify suggests is probably closer to my taste than any of my friends know, right? Certainly my wife or my kids, if they were to, because people don't buy people CDs anymore, but in the old days we did. I frankly would trust Amazon to recommend something more than I would trust my family to recommend some new music to me. And the same thing is true of Spotify and Pandora and all that sort of stuff. And these aren't very sophisticated algorithms, most of these things. I don't think, I think it's like people who listen to this also listen to that. It's mostly that. But boy, the stuff that Spotify recommends is good. I mean, I like a lot of it, not all of it, but a lot of it. I've learned about a lot of new bands listening, by Spotify recommendations. Do we want to say that whatever algorithm Spotify is using in some way understands Rosenblum's taste in music? Well, I don't think very many of us would feel comfortable with that. Like, you know, my friends probably they what they do know of my taste in music, even if it's less accurate or less kind of comprehensive, we would say they know, right? My friend who buys me CDs because he doesn't believe in streaming music, I say, yeah, maybe he doesn't know everything Spotify knows, but he knows my taste, and he knows Spotify. We don't believe understands my taste. My buddy does. My buddy Pete understands my taste, certainly when he buys me a CD, even if he's not as, accurate in some ways. His is knowledge. Spotify's is just this dumb algorithm. Okay. Now, this question has been around forever, right? And God. So this, in the old day, I grew up with Star Trek, the original Star Trek, and there was always an episode, like every few months there would be an episode where, the question would be whether a computer understands or, it truly has meaning. Sometimes they would pose it as, can a computer have emotions? And I know that's been a running kind of, theme through all the various generations of Star Trek. And then there's some great shows on now. God, what did I see? I'm sure you folks know these probably better than me. Devs, right? So Devs, this show? It was on, was it Apple TV? I think, where somebody built this massive, sophisticated computer that took into account, tremendous amounts of data, so it could make predictions about people's intentions and things like that. And at that point, do you say it understands? Oh, I know. I just watched one episode of this. It's called Next. It's on Fox, I believe. And the whole premise is somebody builds a computer that links all the artificial intelligence of all of our items, including our iPhones and our iWatches and all this sort of stuff. And it has sentience, and so it's slowly and horrifyingly taking over the world. So it causes the computer in our car to crash and all this stuff. Okay, all this stuff is, kind of based on these similar questions that Turing asked. Turing was really interested in this sort of stuff back then, as were lots of philosophers, psychologists, and all this sort of thing. And so this idea came up that, Turing posed that it becomes, the Turing test. He didn't call it this, so I guess they did after he kind of posed this question. How can we determine whether computational advice is, for all intents and purposes, understanding what it's doing? Okay, we believe we perceive the world in a meaningful way. That certain things mean certain things that mean certain things to us, right? Certain objects mean certain things to us. We perceive meaning in the world. Do computers perceive meaning in the world? We believe we understand other people's motivations to some degree. Do computers understand this? We have knowledge so we can apply to new, situations in our everyday life. Do computers have the knowledge to apply, right? And what Turing thought is, well, let's think of a kind of a mind game at the time. If somebody could build a computer to fake out a human being that human was actually interacting with a person and not a computer, then it would be, for all intents and purposes, understanding what that person would say. So let me just clear that up. I'm sure you folks know this, but I'm sitting at a computer and I'm part of with this Turing test. What's that? Machina, what's that movie? Oh, I can't remember the one with the whole thing's based on a Turing test, and the guy who is the testee falls in love with a robot and all this stuff. Anyway, sitting at a computer and I'm having one of these, kind of online interactions, one of these chat interactions, and I'm having a really nice conversation with this person. And I absolutely believe that I am interacting with a person, but as it turns out, it's a chatbot. It's this kind of sophisticated artificial intelligence sort of program that is designed to make me think I'm interacting with a person, right? Well, what Turing would say is that for all intents and purposes, if it's faking me out, then it understands, it has some functional understanding of what I am saying, what I am discussing, what we're discussing. Okay, so this is the classic Turing test, right? I know most of you know this, right? If somebody cannot, if a human being cannot determine whether it's interacting with a machine or a person for an extended period of time, for and with some domain of knowledge, then for all intents and purposes, it can be said that that machine understands its domain of knowledge. Okay, that's the idea. Some of the original examples, I'm sure you know this. Eliza, the Rogerian therapist, and for my undergraduate classes, I go through. They all know this stuff too now at this point, but I go through a little demonstration. But you know what it is. Rogerian therapy is just the type of therapy that is often used effectively for crisis counseling. I shouldn't put it down. It can be used effectively, but it's a therapy technique where the therapist just kind of rephrases what the patient just said. So the patient says, I have trouble, I have a trauma from my family or something like that, and a Rogerian therapist would say, oh, it sounds like you have a difficult time with your family. And it's just kind of a way to kind of highlight that the psychologist is listening without doing any overinterpretation, because it's typically used for crisis counseling. One of the first artificial intelligence systems was called ELIZA, and basically it was designed based on this kind of Rogerian therapy technique. So basically the program just had to look for keywords or key phrases and then put them in a response like this. Okay. If you look back at those old artificial intelligence Rogerian therapists, they break down pretty easily. They're not that good. However, probably some of you know there are systems that they have competitions now, Turing test competitions every year, where people design very sophisticated artificial intelligence language programs to interact with a human user to the degree that they might be able to fake them out. And I guess every year a programming group is crowned the winner of the Turing test. And they then put them online for people to play with, and they're great. They really are effective. It's hard to fool them. And yes, you are, of course, by logging on, you are interacting with the program. So, the test isn't actually truly there, but it's hard to actually get them to fall apart and say something nonsensical, right? But you don't even need to go that far. I mean, I think most of us, that's just one way of establishing a Turing test. There's lots of other things too that I think we are fooled with all the time. Certainly, Deep Blue, the chess computer, Watson, the IBM computer that won Jeopardy. These are all machines that can better the intellectual skills of a human. So Deep Blue, the chess computer, that was many years ago. It beat Kasparov. And Watson, the same thing. I guess if you look back at those videos of Watson playing Jeopardy, and actually there may have been a time since I can't remember how many years ago this was now, but there's a very famous footage of Watson on Jeopardy. So Watson's a computer. It has a male voice. Is in the middle position on Jeopardy, and I think the two opponents were both Jeopardy. I see internet connection stable.
Yeah, you froze there for a second.
Okay. Am I okay now?
Yeah.
Okay, thank you. The opponents were Jeopardy masters. There was that guy, that kind of funny guy that's grandmaster, and somebody else. And there was somebody in the back, I guess, typing the questions in for Watson. Or maybe it was doing voice recognition, speech recognition auditorily. I'm not sure, but it was answering the questions. And there were very few times in the week-long matches that Watson was involved in that you could tell it was a machine and not a person. I think there were a couple of, how sometimes in the Jeopardy categories they're kind of puns, right? And there were a couple of times that Watson didn't quite get the puns and it was very literal minded or something like that. But hey, we all know people like that too, right? But for the most part, you ask Ken Jacobs, this Jeopardy master, did you play against Watson as if it was a computer or as if it were a human opponent? And he said, oh no, I got to play against it like it's a grand champion, just like me. And it has an intention to win and it understands what it's doing. Because if I try to kind of think about the computations that might be underlying it, it's not going to help me at all. You know, Jeopardy's fast. You have to go really fast. And for all intents and purposes, Ken Jacobs said he approached it like he was playing a human opponent with desires and intents and understanding and knowledge and that sort of thing. But I wanted to kind of fall back a little bit and talk about when chess playing computers got really good. They weren't quite grandmaster champion level at that point, but they were very good. They can beat most everybody. A philosopher back in the 80s named Daniel Dennett said that there's an important lesson here. Because certainly, I mean, at that point, computer programs, you know, I'm an okay chess player, but computer programs were beating me in the early 80s. My dad was actually a local champion, and they were beating him too. So they were pretty good. And Dennis said, this is Daniel Dennis, a philosopher. He said that, you know, it's interesting. I think when it comes to modernizing the Turing test, I think probably the best way to think about this is not through some sort of, you know, dialogue with Eliza or, you know, one of these kind of chat bots that try to fake you out with answering language with language. Let's just think about something as straightforward as a chess playing computer and think about how pretty much all of us, if not all of us, approach it. And I don't know if you guys ever play chess with your iPhones or anything like that. But you probably would agree with this, that there are three ways we could go about it, Dennett said. The first is you could potentially, in theory, then you're going to see that I think we all approach it the same way, but these are potential ways. Dennett said what we could do is we could take a design stance. So we could try to predict the chess playing computer next move by understanding something about its program. By understanding how it's programmed, how it learns from its experience. So if you are, in fact, the programmer of the chess-playing computer, maybe you'd have some success at thinking about the way it's programmed. But again, most of these computers can change with experience. Certainly Deep Blue did. But he said that it's only going to get you so far because it kind of assumes that the computer is, you know, kind of functionally properly and in fact, you know, kind of doing its algorithms exactly how it was meant to be. Because it's just, you know, it could be that there's something going on with the hardware that could undercut that. So if you wanted to be more thorough, you could, you know, bring in now the programmer and an engineer, the engineer that helped design the silicon chips that are going to be so useful in a chess playing computer. And now what you could do is you could take what he called the physical stance on trying to understand what the chess playing computer is doing. In other words, you can use the programmer for the design stance and then bring in a guy who or a woman who tried to kind of follow the electrical states of the silicon chips to make sure that everything was working properly. And you could do kind of an unraveling of the binary code that way and all that sort of stuff. So basically what you're doing is now tracing the mechanism. And if something's going to break, you know, if it's a computer that's been hot for a long time or something like that, you know, you need to replace the logic board or something, you can make a prediction about what the chess playing computer is going to do then too. But he said, this is not the way that people interact with these things, right? This is just not, I mean, it is, you know, cumbersome. It is ridiculously slow. The way that even chess masters, the best chess playing people in the world, the way that, Ken Jacobs deals with Watson, you know, the grand champion Ken Jacobs, he takes what's called the intentional stance. He basically assumes that the machine, Watson, the machine, Deep Blue, the chess playing computer, is a person with intent, with goals, with rationality, with understanding. And so, what he's basically saying is that as we interact with devices, machines, a lot of the interactions, whether we believe it deep down or not, are interactions that are based on these assumptions. Okay, you know, um, even something as simple as Spotify making, recommendations, and I can fine tune that a little bit and say, yeah, no, I don't like this part of this type of music, the kind of harder edged. I like the softer edged, and then I can tell Spotify that, and then it will recommend softer stuff that's like the music I listen to or something like that. I mean, even at that level, I'm almost like telling it a piece of knowledge that I wanted to now retain and apply in its understanding to making new recommendations. I know deep down, I think, that Spotify's little computer does not understand my taste, does not know what I like. It's just a machine. But boy, for all intents and purposes, I am taking what's called an intentional stance, an intentional description. I am, for all practical purposes, assuming that the machine has mental states, that it has representations that it understands. Okay. I don't have to do that. I can take what's called a physical stance or a design stance to it and try to understand it that way. But no, I don't. By the way, another term for this, I'm just throwing around some terms now, is an extensional description. And it's just kind of, we've been going through this again and again, the mental, the geographical world, the behavioral world, the physical world, the psychological world, all this sort of stuff. Here's another kind of variant on that when I kind of take an approach to a machine that assumes, or that functionally assumes, some sort of understanding, I'm giving it an intentional description, like it has the intent to do something. If I want to describe something that is without mental, kind of function, then I'll take an extensional approach to it. I give it an extensional description. But what Dennett says is, yeah, let's forget that kind of that Turing test. It really shouldn't be the ultimate test. It's kind of fanciful at the time when Turing thought of it. We interact with machines as if they have intention. Okay? We do that, and that means something. That is important for whether we want to say formal systems know. I mean, do we deep down think they know? Maybe not, but functionally we interact with them as if they do. So that needs to be considered as we kind of go through our discussion of what's going on. Okay. Any questions at this point before we kind of shift gears a little bit and talk a little bit about the history of perception and cognition from the computational approach? Ex Machina, right? Is that it? That the name of the movie? You guys know it? Oh, it's good. What else can you recommend where a show addresses this sort of stuff? I bet you guys know tons. Just so I can go watch them.
There's Westworld.
Oh, of course. Of course. Westworld's kind of all about that. Well, yeah, until it kind of isn't. But anyway, yes, but the first season, absolutely. The first season is. And actually, so the solution to for Westworld of sentience is kind of self-recognition through the bicameral mind. I remember that. Okay, well, it's kind of an old theory, but anyway. Okay, what else? Other things I should watch that you think I might enjoy if I'm interested in this type of thing? Science fiction fans, anything?
Have you heard about Person of Interest?
Person of Interest, that has to do with artificial intelligence? Really? I always thought that was a detective show.
It is, but the thing that they're working with is this guy who creates this computer program that he calls the machine, and it's basically like capable of having all of like the sources of information, and it predicts like terrorist attacks and stuff like that.
Is it a good show?
I liked it. It has one of the executive producers is J.J. Abrams.
Sure.
And then the main character is Michael Emerson, who I like. So
Yeah. Okay. I've seen it recommended. I haven't watched it. I'll take a look at it. Thanks for the recommendation. I didn't know that had that component in it. That's more interesting to me.
mm-hmm.
Anything else, folks? Or if you think of anything, you email me. I think this does stuff. Go ahead.
There's a movie that came out a while ago. I think the title was just Her. It
Oh,
was
of
about
course.
this guy who
Yeah.
falls in love with like an artificial
well.
intelligence he talks to through his phone.
Yeah. Has everybody seen that? No. Yeah. Okay. I won't give it away, but the resolution of that, I think, is one of the most kind of powerful and heartbreaking I've ever seen in a movie deal with that. And I don't want to give it away, but it was absolutely surprising. So I don't want to give it away because Mac hasn't seen it yet. But if you ever want to talk to me about it, I'd be happy to. But I think it is in some ways a very real possibility when we end up falling in love with artificial intelligence that it might end in a very different way than we think it will. So anyway, I won't give it a, now Mac's going to go watch it. All right. Anyway, thanks for that, guys. That's really fun. All right, we're going to shift gears here then, and yes, just talk about some very simple stuff, but it kind of is important because it, as I said, oh shoot, what's going on here? Trying to make this bigger. There I am. The reason I make it bigger like that is so when it's on the recording, it shows me a little bigger. Otherwise, it shows me very, very tiny, and it kind of, it's hard to concentrate a little bit when it's that tiny. But anyway, okay, pattern recognition. So what we're going to do now is move away from the philosophy a little bit, from the, kind of the conceptual stuff underlying the computational approach. And now we're going to spend certainly the rest of today's lecture and probably much of next lecture talking about some of the kind of examples of computational approaches, some old, like this one, and some much newer that will kind of help fill in some of the kind of newer material I want you to learn from the course as well, not just the history. Anyway, let's talk about the history right now. And this actually, all this stuff came out around the same time as people were really pushing this computational approach, 60s, 70s, 80s. The idea is pattern recognition. And the question is, how does the brain recognize patterns? Typically, it's done visually. And so here's a pattern in front of you now, the letter R for Rosenblum. The question is, how did your brain recognize that? Well, one way it could, in principle, is through taking in that image, say it's being reflected on the back of the eye, and going through some sort of process where it looks for stored memories of images somewhere in the brain until it matches, right? So I could have stored images of all the letters of the alphabet in my brain. And so what I'm going to try to do is match that input to what I'll call these memories templates of the letters that are in my brain. Okay, so in comes this image, and at first it can't be recognized, but I'll first match it to the template I have for the letter A, the template I have for the letter B. Of course, this is instantaneous, right? It's super duper fast, but eventually I'll get to R and saying, ding, 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 that's the letter R. And I need to do that, of course, for every letter that I'm being presented. So I can do it here, and I have got to get the rest of these letters by doing this matching. Okay. Again, let's assume that it can be infinitely fast, and we have an infinite amount of templates, because very soon we're going to have to, broaden the templates just from letters, or letters that look like this. But let's assume that we have that. Just in principle, we're talking about how this might work. So this is the template. Template matching process. And in principle, it does work because, in fact, there is a machine that works like this that we use fairly regularly. I mean, we used to use it much more regularly. But the numbers along the bottom of your check are recognized through template matching. Okay. Now, I just was going through these notes the other day, and I realized this is an old slide. Clearly, it's from 1991, and really, I made the slide. You can see the date here. I was living in Massachusetts at the time. That's when I made this slide. I wanted to show the students an example of template matching, so I put a copy of my check there. And it was just after Donald Trump's first bankruptcy, where it was clear that he had made some really stupid decisions, and so it was a joke that I was going to loan him money in 1991. Little did I know, right? At that point, it should have been enough for us to know. But anyway, that's not why. So Donald Trump's name is there from a 1991 event where he went bankrupt. Okay. Anyway, the idea here is if you look at the bottom of checks, and they pretty much still look like this. They are numbers, they're digits that are very distinct from each other, right? I mean, these don't look like normal digits. A 1 could not be, is there a 7 in there somewhere? No, but I'm trying to think of things that might, like a 4 does not look anything like a 2. The zeros look nothing like an 8. I mean, they are very, very distinct, these digits. And there only need to be, let's see, I guess there's the 9 digits plus 0, 10. And it looks like there's a couple of more things it needs to have in here. I guess whatever this thing would be called, a colon and a line. It was this a dash here, something there. I mean, but we're talking about a handful of templates that are, in fact, part of the memory of the little device that reads checks. So, when you put your check into the ATM or you give it to the teller and they scan it under a little kind of device, there is something like a little, camera there that reads the bottom of your check to determine the account. So the account's in there, the check number is in there, and the bank's in there, I believe. I believe that's what all this stuff is. Okay, and so it can determine where it's going to take the money from, and where the account is, and all that sort of stuff. It works. It absolutely works, and it's worked forever like that since probably the 60s or 70s. It's worked like that. Question is, can we work like this? And it's very obvious that it's going to be a problem very quickly, because how is this designed? This thing is designed to deal with images, patterns that are designed to be extremely distinct. It is also created so the scanner is always the camera is always looking at the check from the same distance and the same angle. It's straight down. Okay. So you don't need many templates for this to work, and that's absolutely why it works. But we know, of course, that we are dealing with, just very quickly, lots of different types of things that we can even categorize as a specific letter, such as letter R. We are able to, see all those things with the letter R. Maybe this one's a little tricky, the one here, the cursive little one here, but for the most part, we would say those are all R's. And so what does that mean? Well, maybe we have little templates that represent all these R's that we've ever seen, right? That could be how it's done. But, very quickly, you just realize that, as you're looking at this slide on your computer, you're probably looking at it at a different angle from where I'm looking at it. And I can tell you right now, whether I look at it from here or here, those still look like R's. In other words, what it would suggest is that if this were strict template matching, I would have to have a template for each of those R's seen from all these possible angles. Okay? And so what I'm doing here is this, by the way, is called shape constancy sometimes. It's related to shape constancy, I should say, that we perceive objects as being constant shapes, even though what's coming on our retinas is, in fact, a different shape of the proximal stimulus. Same with the door here, and same with these letters. Every time I move it just a tiny bit, in fact, just the little saccades of my eye moving back and forth, I am getting a very subtle but important different perspective on it, suggesting that if I've got templates, if all this has to do with template matching, where the thing that is coming in has to pretty much exactly match the template I have in memory, I need the number of templates has grown exponentially, right? And not only am I seeing them R's when I'm standing here, I see them as R's when I look close. I'm sure you appreciated that. Or if I stand way back here by the Tower Bridge of London, I can still see them as R's, meaning that the size of the retinal image has changed. And if that's the case, then how am I matching to those templates that I just described to you? There've got to be templates that are not only, for example, this letter R from a certain position, okay, left, right, but this little R, there need to be separate templates for every possible size I would see that letter R. So size constancy, certainly we see that as an R, or you see this as a iPhone shape, rectangular shape, whether it's really close or whether it's far away. And therefore, we've then increased the number of templates even more. And then finally, we're just talking about letters. Letters are, probably not what we evolved to perceive, right? We perceive to perceive 3D shapes, including faces and all the complex stuff that we come upon. Okay, there's a very old picture of me. All right. So how do we do this? Is template matching going to work? And the answer is simply, it's very clearly not the way I've described it. Back historically, when people were talking about this possibility, they said, well, maybe what happens is it is template matching, but possibly when the image comes in, it's not right away matched to a template, but some sort of pre-processing. Oh, right. The first possibility is we have an infinite number of templates. No, we can't. Maybe pre-processing or normalization occurs. In other words, this R comes in right here, and possibly what happens is we make sure now that it's kind of perpendicular from whatever in the brain has to interpret it. So yes, I'm looking at it here right now, but it comes in and I'm going to reorient it so it's perfectly perpendicular, and then I make it the right size so it has the potential to match the templates that are of a specific size. And then to make sure it's an R, I cut off all the non-R stuff, like this little curly Q in its hair, this little curly Q back here. I cut off everything that doesn't look like an R, and now it's ready to match a template. Now I can go ahead and try to match it to all my letter templates. Okay, that's that had been suggested as a way you could still maintain a template matching model and deal with all this variation in the input. The problem is, and I'm sure you're thinking of this, is how does pre-processing and normalization occur? How does the system actually know to cut off things that aren't R-like without knowing it's an R, right? It's just begging the question, right? How does it know to orient it so it's flush without knowing what it is? And so it's completely unclear on what basis it could possibly be doing that pre-processing before the template matching occurs. Okay, and that's just for letters. Imagine what it would be like for faces, right? These faces are fairly easy to recognize because they're being shown straight up, but we often don't see faces, at least in the real world, when they are kind of just looking straight at us, or we get such a frontal view of faces. And also, faces move, right? So how are we going to pre-process all that information away? Clearly, it's not going to be a very effective way. Clearly, we're going to need a much more flexible way of doing this, which led to a pattern recognition solution that is much more common and is still, to some degree, considered an important part of the perceptual process for modern theories, and that is feature analysis. So what feature analysis is going to do is not try to match images to templates right away. It's going to break the image down into features and then try to kind of evaluate those features to find which template in memory the image best matches. Okay, so yeah, there's still kind of templates, but you'll see that they're of a very different nature, and the process is completely different. So sometimes this, by the way, in the old days, it was called a structural description. I actually haven't seen that term in a long time. But the idea is that the process is going to do a description of the structural components of the input. Okay, so of the letter R, we're still seeing here's the letter R. Yeah. We're still seeing a letter R here. And rather than trying to do a template matching on that input as a whole, the first part is going to involve analyzing the features, analyzing the structure, doing a description of the structure that then can be evaluated for something like a matching later on. So what are the features of that input? Okay, what are the features? And we can just do this very kind of superficially just to come up with some, just so we understand what they mean, but you could clearly come up with more features in this. So what do I see here? Well, I see a vertical line right here. So my little vertical line, right? My little vertical line feature detector, feature analyzer could say, hey, guess what? I see a vertical line. What else could we do to describe this? I see a semicircle up here. It's not a full circle. It looks like the semicircle is kind of making contact with that vertical line right here. See? Okay, there's a semicircle. There's a vertical line. Cool. I see a slanted line right here. And I see that where the semicircle intersects the vertical line, what we have there is two right angles. Just the way this R works, we have two right angles. Okay. And from that kind of structural description, that description of the structure, we can then take in this data essentially and establish that we have the letter R. And what we're going to do is, starting next class, is talk about how that might occur through a very simple model that, in fact, the mail system in your post office works with, a feature analysis model. Okay, so we'll talk about that next week. Have a good week, and I will see you then.